mathematical model of a pressure process. Mathematical model of a typical pressure process. Pressure process is pressurized vessel. And the pressure inside the vessel will be controlled. This is the pressure process. Here, you can add a valve here, a pneumatic valve. Its opening varies from M. The inflow rate is Wi. Outflow rate is W0. So many kg per hour. This is also per kg per hour. Mass flow rate. The upstream pressure is Ui. Downstream pressure is U0. The pressure inside the process is U. The U is the process variable to be controlled. This is the process variable to be controlled. How to control? By controlling the inflow rate. How inflow rate can be controlled? By adjusting the valve opening. Therefore, the inflow rate is the manipulated variable. Valve opening is the manipulated variable. By manipulating valve opening, we can adjust the inflow rate so that the pressure inside the process can be controlled. For this, we have to apply conservation of mass. That is mass inflow rate minus mass outflow rate equal to rate of change of mass inside process. For this, what we can write is, we can write mass inflow rate is Wi minus mass outflow rate equal to W0 equal to C du by dt. The mass inside the tank is a function of pressure. If you multiply by this gas constant, where C is the gas constant. But Wi equal to function of Ui, that is upstream pressure. This is called upstream pressure. This is called downstream pressure. It is function of Wi is function of upstream pressure, downstream pressure. As far as inflow rate is concerned, this is the downstream pressure. As far as inflow rate is concerned, U is the downstream pressure. As far as outflow rate is concerned, U is the upstream pressure, U0 is the downstream pressure. If you consider the overall process, Ui is the upstream pressure, U0 is the downstream pressure. If you consider inflow rate alone, then Ui is upstream pressure, U is the downstream pressure. Therefore, Wi is function of ui, u and parallel opening, that is m. This is a nonlinear function. Nonlinear function. So to linearize that, let us total differentiate this with respect to, let us total differentiate this. What you will get is dou f by dou ui dui plus dou f by dou u du plus dou f by dou m dm. This is total differentiation of this function. But f is nothing but wi. F is nothing but wi. A function, that's all. But we can consider this, the relation between inflow rate and upstream pressure ui. If you consider that, it will be a nonlinear relationship. So we have to find a linear relation between upstream pressure and wi. For that, we have to consider the nominal operating point. At nominal operating point, ui nominal. At nominal operating point, the inflow rate is wi nominal. At this point, if you draw a tangent to this graph, this gives a linear relation. Linear relation. So for small changes about nominal operating point, instead of considering small changes about nominal operating point, we can consider this linear relationship instead of nonlinear relationship. That is called a linearization. So to find that linear relation, what is the resistance at this point? What is the slope of this line? Slope of this line is dou f by dou ui. Let it be ri. Similarly, if you consider the downstream pressure is u. As far as wi is concerned, downstream pressure is u. If you draw the relationship between u and wi, the relationship will be like this. Here in the bottom, if you see that it is a vertical line, it means there is no further increase in, even if you decrease the downstream pressure, there is no increase in flow rate. Instead, it is independent of decrease in pressure. That pressure is called critical pressure. Below that critical pressure, it becomes independent of downstream pressure. So here also, we are not going to operate at this region. We are going to operate here at a nominal operating point. This is u nominal. This is wi nominal. At this, if you draw a slope, you will get like this line. This is the slope. This is linear relation. This is linear relation. So we are, instead of considering this nonlinear relation, for small changes at this nominal operating point, small changes, we can consider, instead of this graph, we can consider this linear relation. Therefore, the linear relation here is by knowing the slope dou f by dou u is Ra. Let us assume that it is Ra. Therefore, this at nominal operating point, dwi can be written as delta wi equal to dou f by dou ui at nominal operating point is Ri. Dou f by dou u by dou wi. Wi is equal to f. That's why we can write 1 by Ri. We can write 1 by Ri delta ui plus dou u by dou f, that is dou u by dou wi is Ra. Therefore, 1 by Ra delta u plus dou f by dou m, that is dou m change in valve opening, change in flow rate, that is gain kv valve gain to delta m. But this delta wi change in inflow rate can be written as small wi equal to 1 by Ri. Delta ui can be called small ui. This is caps ui. Delta caps ui equal to small ui. Let us assume 1 by Ra u plus kv small m. So we got one relation for change in inflow rate. Similarly, we can write for another relation, that is w naught equal to, that is w naught equal to function of u comma u naught. For outflow rate, u is the upstream pressure. U is the upstream pressure. For that, for u here, for inflow rate, u is the downstream pressure. That's why this graph. For outflow rate, u is the upstream pressure. That's why graph will be like this. This slope is RB. RB. This slope is negative. That's why minus RE. This must be considered as minus RE. Minus RE. Because negative slope. Negative slope. Here positive slope. Positive slope. Therefore, this must be minus. Here it must be minus. Now, this is positive slope. That's why plus RB. This is this is for outflow rate and upstream pressure. That is U. U is the upstream pressure. This U is the upstream pressure for outflow rate. Similarly, for downstream pressure, U naught, W naught, this is the slope. Let it be R naught. This slope, that is dou U naught by dou W naught, that is equal to dou U naught by dou F, or dou F by dou U naught. Therefore, we can write W naught equal to function of upstream pressure, downstream pressure. Therefore, total differentiation dW naught equal to dou F by dou U du plus dou F by dou U naught du naught. That is the total differentiation. At nominal operating point, this is approximately equal to delta W naught equal to dou F by dou U. For W naught is dou F by dou U is RB. So we can write 1 by RB, 1 by RB delta U plus dou F by dou U naught is R naught. That is negative. That's why we have to put minus 1 by R naught, 1 by R naught delta U naught. But W naught is small. W naught equal to, for changes, change in W naught can be written as small W naught, 1 by RB small u minus 1 by R naught U naught. Let it be 2. From 1 and 2, we can write the first equation again. What is the first equation? This is the mass balance equation. A becomes, using 1 and 2, A becomes W. What is the A? Wi minus W naught equal to C du by dt. But Wi can be written as Wi nominal plus Wi change in Wi minus W nominal minus W small w naught equal to C d by dt of u nominal plus change in u. So, but at nominal operating point, the nominal inflow rate equal to nominal outflow rate. Therefore, these two getting cancelled. And this also equal to 0 because it is a constant. Therefore, the equation becomes for changes Wi minus W naught, change in outflow rate, change in inflow rate minus change in outflow rate equal to C du by dt. This can be substituted from 1 and 2. We'll get one says what 1 by Ri, Ra, and Kv. 1 by Wi equal to 1 by Ri Ui, then plus 1 by Ra U plus Kv val gain multiplied by M minus W naught equal to what? W naught from second equation we have to write. That is equal to 1 by Rb U, 1 by Rb U minus 1 by R naught U naught equal to C du by dt. Here 1 by Ra is negative, no? Because of negative slope, Ra is negative, 1 by Ra is negative. Bring all u to the right hand side. What you will get ui upon Ri plus kvm plus 1 by R naught u naught equal to C du by dt plus u by R A plus u by R B. Now, if you take Laplace transform, you will get ui of s upon Ri plus kv gain, val gain multiplied by m of s plus 1 by R naught u naught of s equal to Cs plus 1 by Ra plus 1 by Rb multiplied by u of s. Here, if you manipulate m of s, you can manipulate u. But ui and u naught also plays a role. These two are playing as disturbances. Disturbances. This is also a disturbance. If upstream pressure increases, flow rate will increase. Upstream pressure decreases, flow rate will decrease. Downstream pressure increases, flow rate will decrease. Downstream pressure decreases, flow rate will increase. And if you manipulate M, flow rate will increase and pressure will increase. If you assume that ui and u naught are constant, then the transfer function is u of s output, that is pressure inside the vessel, the variable to be controlled. This is the process variable, already told. This is the process variable to be controlled. U of s upon m of s equal to kv upon cs plus 1 by Ra plus 1 by Rb. This is one model. Suppose, let us assume that the valve is not changing, valve opening is constant, and downstream pressure U naught also constant. If the upstream pressure is varying, means you can get a disturbance model, that is U of s upon U I of s equal to 1 by Ri upon Cs plus 1 by Ra plus 1 by Rb. So that we got. So in that case, this is 0. This is also equal to 0. The third case is there is no change in UI. Change in UI is 0. Change in valve opening is 0. But U naught is changing. Then it is called disturbance model. U of S upon U naught of S equal to R naught upon CS plus 1 by RA plus 1 by RB. So what we can get is the first model is the input is M of S, valve opening. The output is U of S. The transfer function is KV upon CS plus 1 by RA plus 1 by RB. Another model is disturbance model. The disturbance model is the input is UI of S. The output is again U of S. But because of change in upstream pressure, that is equal to Ri upon CS plus 1 by RA plus 1 by RB. The third one is you can define another model for change in downstream pressure, that is U naught of S. For that, what is the change in U of S? The model is R naught upon CS plus 1 by RA plus 1 by RB. This is change in U naught. For change in U naught. Now, if you add all these together, if any change is there, you want the total change means you can add them all together. This also can be added. This also can be added so that the output is U of S. If any change in MS, you will get change in U. Any change in UI, you will get change in U of S. Any change in U naught, you will get change in US. This is the mathematical model of pressure process. Pressure process doesn't mean that it is a vessel. It may be a furnace. For example, Naval Lignite Corporation, a furnace will be there. It is of 6 floor heights and a very big area inside. In that, the waters will be in tubings. Water tubings will be there. In that, furnace will be there. But in the periphery of that furnace, a 6-floor building like that, in the periphery of the building, there will be instrumentation is there. But the insulation for heat transfer insulation is there, even though if some windows are there, the flame won't come out because the pressure inside the furnace is maintained negative than atmospheric pressure. That's why the flame will not come out through that window. Even you can open the window, you can see the flame, but it will not come out because of the negative pressure maintained inside the furnace. That is also pressure process. Even furnace is a pressure process. We have to maintain the pressure inside should be less than the atmospheric pressure. So it is also a pressure process. Wherever we are maintaining the pressure, that is called a pressure process.